Hey Paco, how's it going?
Hi, Tyler. I'm trying to fix my camera. It keeps falling down.
I can see that.
Yeah. Oh, that's so annoying.
The ceiling view. Classic. Classic Zoom
Yeah.
mishaps.
Yeah.
I'm
How are you?
good, thank you. Good.
Good to
Uh,
hear.
say what?
Good to hear.
Yeah, for sure.
Whew.
So what are you planning to take in the fall?
8430. The rational
Daniel's
points of
class.
variety.
Yeah,
Yep.
nice.
Yeah, I talked to him. He did say I might have to brush up on my algebraic geometry, but he said go for it.
Right. You said that, I
Yeah,
remember.
I had an honest talk with him, but he said go for it.
Yeah, go for it. Yeah, might as well, just be
Yeah, so
ambitious and take it. At the
yeah,
same time, you'll, yeah.
yeah, so I'm studying. I'm trying to self-study algebraic geometry again.
Yeah, because in the fall they're offering AG, right?
No, they're not. Apparently, I
Oh,
misread. It's really
oh,
only every 2 years. I was
what?
hoping they'd offer it.
Yeah, I thought they did change that for this year.
I
Oh,
don't know, but I saw there are no like slots. If there are slots, I will take it. But right now, it's not open for registration. And as
that's
far as I don't know.
yeah. I could have swore they had it. They're offering it, but if they're not, that's unfortunate.
Well, it's in the offerings, but it's like it's grayed out. So I'm assuming nothing is going on.
I see. Yeah, I looked on. I had the my UGA open right now, so I just checked it. It seems like it's just TBA, no instructor or anything. So it
Yeah.
might not run. Um, oh well.
Yeah, it's kind of. Well, I guess they assume that everybody comes here knowing AG, so they don't offer it more than.
But that is so untrue though.
Yeah, and the thing was, it was offered last fall,
Right,
but
right.
I wasn't here last fall yet. I wasn't here yet.
Yeah. That's strange because they offered it the previous fall, like 2018. That's when I took it. So
Yeah,
like
What are
they
you
offered it.
talking about? Intro to AG?
yeah,
Yeah, exactly.
Yeah, I think it's offered every 2 years is usually.
yeah.
Yeah.
So it'll probably be offered not next year, but the one after, which yeah, that's unfortunate that you weren't here this fall.
I
Okay.
know.
But
Yeah,
they offered it last fall, you said, Paco? Was that it?
Yeah.
yeah. 2020.
Yeah. So, but then they also wait one sec. Maybe I got my thing mixed around. Oh, I see this fall. I see what you mean. Oh,
2020.
okay. I was
Yeah.
thinking like the year before that. I was like in my third year they offered it. I don't remember that. Okay, yeah, because then it'd be every. Okay, good. Yeah, they
Yeah.
should offer it every year though. I mean, I don't know. Maybe it's just me. I wish I took it like in my first year instead of my second year. That was my personal qualm with that.
I can't be taking it in what's like practically my third year. So I just have to learn everything myself now.
Yeah. Well, that's true. So I usually do it, right?
Yeah.
You know.
Sometimes it's better though, because you learn the way you want to learn, right?
Mm.
But their age either it's one of those things that's wide and shallow, so you have to know what you have to pick up.
Yeah.
Mhm.
Yes,
Intro
but there's also
AG.
the other thing that you might end up with an algebraic geometer, and you might not want to learn that, that part where they do like Riemann surfaces and things like that, right?
I'm actually looking more into analytic stuff, but for the algebraic, I need algebraic stuff and I need AG for that
Mm.
at some
Mhm.
point.
Do you have a feeling for like who you might want to work with?
Yeah, I do.
So who is it?
Paul.
Paul, of course. Yeah, cool. Yeah, Paul's cool. Very nice.
Oh, there you go.
Hey, hello everyone.
Hello.
Just a warning, I had such terrible connectivity issues this morning. I had to log in and log out
Oh no.
several times. Still says my internet connection is unstable. How does it look to you?
You're a little choppy.
Yeah.
Actually, you guys look a little frozen. Is it okay?
It's a bit laggy.
It's choppy.
Can you hear us?
Choppy.
Okay.
Uh, I can hear you now. It's really choppy. Actually, on my other laptop, it worked better. That's good at all. I think let me reboot this laptop and see if that's.
Oh no, how did I become the host?
Walker, you're the host. Start teaching Galak homology. Come on.
Oh no. Oh no. How did they? Is it random or is it because I'm first alphabetically?
Yeah, I'm not sure. One other comment on the intro to AG thing though, Paco.
Yeah.
Are you planning on taking commutative algebra? Is that being offered next semester?
If it is, I'll take it, but I don't think I saw it being offered.
I think.
It's in the spring. They're offering commutative algebra.
And it's Daniel?
Yep. Yep.
Okay, so you might get some AG from taking that.
Yeah. I mean, I've bits and pieces. I've done an elliptic curves course back home, so just very basic stuff. Like whatever you find in Silverman. And actually black boxed a lot of it. So
yeah. Yeah, the first chapter is a good reference, but yeah, it's a lot of black box stuff.
Yeah. Thanks for the tips. Now I know what to keep in mind.
You know also that Alvaro had a class this semester.
Yep.
And he did elliptic, right?
That? Come again?
So
Yes.
Alvaro Rosano Robledo, he was teaching elliptic this semester.
Yep.
And he had, I think he even posted videos on YouTube.
Yep.
So that might be a good place to start with AG. Because elliptic technically are AG, right?
Yeah, that kind of stuff I do know.
I see.
Because I did an elliptic curves course at home after Silverman and Tate.
I see. So why then do you need, if you're doing an analysis, why do you need more AG then?
No, it's like for some of the algebraic geometry stuff. like later on.
I see. Because I don't think that, Paul will ever use Riemann log, for example, in his
yeah, it's kind of funny that Paul is teaching algebraic geometry, algebraic NT right now, but his book's really, really good. Yeah.
I know there's a guy though that does, I think his name is, I forget his name, he's at Columbia and he gave a talk where he does analysis, but he also does attack of homology somehow, and he really cool stuff, but they're hard though.
Interesting.
All right, I'm back. Is it better?
I think it's better.
Okay, good. All right, that's actually one thing I didn't try in the morning. I did everything else. Okay, well, let's try to get back into it. Hope it works. Hope it works out. Yeah, so there was some stuff on kind of Galois homology of divisors and stuff over function fields. I think that's the least of our worries. So I think I just don't want to return to that material because I have so much other material to speed through. So yeah, what was that? Just this little corollary. Yeah, I don't even know. We'll see. We'll see if we even get back to using it. In fact, but it's easy. It's easy to prove. Okay, so let's still. We'll see. So let's just get a look. Yeah, I can make that a little bigger. Great. Okay, so I want to talk about Galois homology of the Adel class group, okay, which is kind of, it should be reasonably clear why we're talking about this, because the Adel class group is supposed to be our target group for global class field theory, just in the same way that the multiplicative group of the field was our target group for local class field theory. And so our approach to class field theory is coming in particular kind of out of this Tate Nakayama result, right? So you may want to flip back and look at that. So it was, we wanted some we wanted some G modules so that the first cohomology vanished, and then there was some kind of fundamental class that had nice properties with respect to the second Galois cohomology, and then combining those two things already gave us this reciprocity map, which was an isomorphism from the norm cokernel to the abelian Galois group. Okay, so the broad outline is that at that level the outline is the same. So that's why we're interested in Galois cohomology and the Adel class group. Okay. So first, a little bit of local global number theory stuff. So I have a global field, K-sep, I will use to denote the separable algebraic closure. Harari denotes that by K-bar, but he still means the separable algebraic closure. So now let me do something that is actually commonly done. So for each place of my field, I look at the separable closure of the completion. Okay, so like every algebraic extension of a complete field that has a unique valuation, okay? And because it's separably closed, then it's going to contain a copy of the separable closure of K, because it's going to contain K and it's going to be separably closed. And so I can choose, I should underline the word choose here. There's like a uncountable amount of choosing, in fact, no countable amount of choosing to, I can't decide. There's at least an infinite amount of choosing to choose this field embedding. I think I had it right. I think it is an uncountable amount of choosing. Anyway, once I do that, if I restrict the unique valuation on the separable closure of the completion to the separable closure of K, well, you restrict evaluation, you get a valuation. So that gives me a distinguished place of the separable closure lying over V. And again, there's kind of a profinite or a tree structure. If I went from K to some finite separable extension, then I would have finitely many places lying over V, but in general, the number of places would increase, increase, increase. And so the structure of the set of places of the separable closure lying over a fixed place is kind of naturally an inverse limit of finite sets. Okay, so that's kind of a profinite set itself, like a big uncountably infinite set. And via this maneuver, in some sense, you could think of this as being like some kind of infinite branching tree, and I'm choosing a root of the tree if you want to. Am I choosing a root of the tree? I'm choosing a path through the tree. Okay. Anyway, and so by doing this for every separable algebraic extension, by restricting my distinguished place on the separable closure, I get a distinguished place of the extension. So following Harari, I think I'm just going to call that V bullet. Okay. So if I have a Galois extension, then by GV, I mean the decomposition group at this distinguished place. Okay. Which, as we reviewed, is also the full Galois group of the Galois extension of completions. Okay. Again, though, the thing we're doing, because we made this choice, I should be saying something like G of W, where W is an upstairs place, but somehow I managed to canonically choose an upstairs place. All right. And so here I'm reminding you something. Harari doesn't quite say this, although he says things which are kind of equivalent in content. This is from my number theory 2 notes. If you take a finite degree separable extension of global fields, first of all, most importantly, there is a natural ring embedding from the K adels into the L adels. Where is this coming from? This is coming from the very basic fact, which is sort of central to number theory 2, that if you make a finite degree separable extension of a field and then you tensor with the completion, then you get the product of all of the completions of the places that lie over that place. And so if you sort of think that through, that is going to give you, that kind of explains how you're mapping AK into AL. Well, on the one hand, here I have a product. Here it's kind of like a diagonal. Each piece is like a finite diagonal embedding. So for each V, I have a KV that I embed into the product of LWs. Okay, and so I can do that, and I can really do that because I have this map is isomorphic to that product, and so I can just, one tensor KV has a copy of KV in here, and so in a very nice way you can embed KV into this product. And again, this embedding actually induces an isomorphism from the L adels to just the K adels tensor. Okay. And again, this kind of looks, by the way, from our perspective, this kind of looks like, maybe if L over K is Galois, this kind of looks like AL is induced from AK in the sense of induced modules, and that will come up later. Okay, and so for a lot of what I'm doing, I'll have a finite extension with Galois group G. Okay, and so now for any downstairs place, I'm going to take it's just a definition, the kind of V part of the adels. And so despite the fact that I'm putting a K on it, this is an upstairs guy. This is the product of all the upstairs completions that lie over this downstairs place. And again, that's where this tensor product thing is helpful, because what is this? This is literally the unit group of the, I mean, you can see, right, if these are isomorphic, take the unit group, that's what you'll get. Okay, and then inside there you can take the integral unit group. Okay, and so what's the point? First of all, the Galois group G acts on the set of places lying over V. We mentioned that already, and it using that action, or it acts on IK of V, and in a way that that stabilizes UK of V. And again, thinking of IK of V as this, I think is a really nice way to understand how the Galois group acts, because the Galois group acts on this first factor here, and then it acts trivially on the second factor. Okay, so the action on this is literally induced, if by induced I mean tensor product, from the action of G on L. Okay, so that's what that action is. That's fine. And again, if you stop and think about it, then under that action, the things that are everywhere have valuation 0 are certainly going to be preserved. Okay, and again, yeah, so by the way, this lecture is going like super fast and super superficial. So I regret that, but this is what we have time for. So if you stop and think, you can probably convince yourself that this means that that this IK of V is literally the induction from the decomposition group to the group itself of KB star, and UK of V is literally the same induction from the local unit group. Okay, so this gives some hint as to why the Galois cohomology of the adels is going to work out nicely. All right. So, oh, right. And so then the other reason why it's nice to bring up, why am I bringing up these IKs and UKs? In fact, you could just by, so what am I doing? Like I'm taking my restricted direct product, and then I'm just kind of bundling together the finite set of places W that lie over a single place V. And so I can bundle it together that way if I want. And if you stop and think about it, then the IDEL group upstairs is also equal to the restricted direct product of each of these IKs of V's. Again, it's the restricted direct product of all the LW stars, and if I want to collect finitely many of them together, okay, it doesn't do any harm with respect to the this family of compact open subgroups. Okay. Well, I guess. All right. Well, I guess it's equal to that at the, at the non-Archimedean places. Yeah. So here, yeah. So it's equal to this if the place is non-Archimedean, and then it's equal to, well, whatever. It's equal to the same thing. UKV is just equal to the full IKV if V is Archimedean. Okay, that's hard to see. Anyway, so, okay, so yeah, so this is just a nice way. In particular, this makes very clear that the upstairs Adele group is a G module, okay? Because G is acting on each one of these guys, and then because it's a restricted direct product, it's a direct limit of products. All but finitely many factors live in the UK, and so then G acts diagonally on each one of those products. Sorry, that was my doorbell. Let me just check for 1 second. I'll be right back. Okay, well, happy 2021, everybody. All right. Okay, those are for later. All right. So right, so we have a Galois module structure on the Adel ring, for that matter, but more pertinently to us, we have a Galois module structure on the Adel group. Okay, we're more interested in the Galois module structure on the Adel class group, but we're getting there. Okay, and so now come a bunch of results, very few of which are going to get any explanation or proof in this lecture, but I'm showing you where they occur in chapter 13 of Ferrari. So throughout this lecture, either, for the most part, L over K will either be a finite extension with Galois group G, or it'll be a finite cyclic extension with Galois group G. So you'll have to pay attention to see which one it is. Okay, so first of all, as you might hope, so the upstairs Adel group is the Galois module. If you take the invariance, you get the downstairs Adel group. Okay, good. I don't think that's very hard to prove. Moreover, the Tate cohomology of the Adel group is very nice. There's purely, I mean, it really is just the direct sum of the Tate cohomologies of the localizations. Here you see that I'm using this convention here where I'm choosing, so this GV is the, is the local Galois group. It's the Galois group of any completion. Yeah, maybe there's something, maybe this is a good time to say, since the extension is Galois, in general, there will be, of course, several places W of L lying over the place V, but because it's Galois, each of the completions are going to be isomorphic to each other, even as a KV algebra, right? That's just the Galois symmetry is acting on all these. And so the point is, it really doesn't matter which place we chose. If I just wrote any LW here, if I wrote LW for any W lying over V, and if by GW I meant the decomposition group of the place W, which is isomorphic to the Galois group of LW over KV, these groups are all the same. Okay, so it really doesn't matter which place I'm using, which upstairs place I'm choosing, because the extension is Galois. Okay, so that's the first result. And then the next result is that it follows from this that, first of all, the first Galois cohomology of the Adel group is equal to 0. Why is that? Well, you can see that because it's isomorphic to all of these. And just Hilbert 90 says that all of these H1s are equal to 0. Moreover, the third Galois cohomology is equal to 0. And that does follow from Tate-Nakayama stuff, which I'll let you think about. Okay, let's see. And so because the invariants of the L Adels are the K Adels, of course, from our general machinery of Galois cohomology, we have a norm map. Okay? So we always have a norm map whenever we have a finite group acting on a module, right? And so, so this is the norm map that I was careful. Remember, I had this like thing that I was calling the adelic norm, and then I changed my mind and called it the adelic absolute value because I was also going to have some kind of relative norm map, and here it is. Okay. And so as you, what's the norm map? Well, what's the norm map ever equal to? You take an element to the product of the product of all the group elements acting on that element, and as ever, the norm evidently. Oh, some crazy stuff is going on here. All right, never mind. As ever, once you take the norm, it sticks you inside the invariants, and the invariants are IK. So okay, so that's our adelic norm map. Okay, what's this next lemma? This next lemma is it's very easy to understand what the image of the adelic norm map is. Okay, again, we really want the norm map on the adel classes, so we're not, this is not doing anything definitive, but this is a good first thing to say. So you are an adelic norm if and only if everywhere locally you're an adelic norm. Oh, here's where I made the remark that I made up there. So again, it doesn't, again, it may look a little bit weird to say that I'm a norm from this distinguished completion. V bullet doesn't matter. If you're a norm from 1 kW, you're a norm for W lying over V. You're a norm from every kW for W lying over V, because again, they're isomorphic as KV algebras. Okay, so this is a very simple. That being an adelic norm is nothing else than being a norm everywhere locally. That's nice. Okay, so then for reasons that probably are not going to get paid off in this very brief lecture, we can pass to the limit on the adel groups, and we just get I, which I will call the geometric adel group. Okay, it's kind of a reasonable thing to do. And then I can also pass to the limit on the class group side. So inside this direct limit, I'm going to have the direct limit of all finite Galois extensions of K, and the direct limit of all finite Galois extensions of K is the separable closure of K. And so if I mod out the geometric adel group by the units in the separable closure of K, then by definition, that gives me the geometric adel class group, which is also seen to be the limit of all the class groups of L. Okay. All right, next proposition. If you have a finite G-Galois extension, then also the invariants of the class group are what you would want. Okay. I don't think this is a difficult proposition. Yeah, so the invariants of the L adel class group or the K adel class group, oh, and then here, this maybe looks like the previous, it's very similar to the results that I said before, but here I'm just passing to the direct limit. So I think these things follow from what we said before, basically just by passing to the limit. And so if you take the invariance of the geometric adel group, you get the K-rational adel group. If you take the invariance of the geometric class group, you get the K-rational class group. Okay, so that's no easy to absorb. Okay. And let's see, more results. Yeah. So the next result is for all the cohomology groups. Yeah. So this result, let's see. Looks similar to, yeah. So before I stated this result for Tate cohomology of a finite Galois extension. And now in a similar way, I'm sort of passing to the limit. And for whatever reason, I'm only taking I greater than or equal to 1. But again, probably this result just comes from passing to the limit on the previous result. And so again, the cohomology groups of the adel group really just come out in terms of the cohomology groups of the unit group on the local fields, which are well understood, in particular by Hilbert 90. The first Galois cohomology of the adels is equal to 0. Okay, but again, we really, that's all well and good, but we don't really care about the Galois cohomology of the adel group. We really care about the Galois cohomology of the adel class group. Okay, so now we continue. Now we begin the study of this, or by study, I mean I'm going to very quickly tell you some results. Okay. So the first thing, so really where are we going? We would like to understand, so if I have a, again, if I have a Galois extension L over K, I would like to know what the Tate H0 on the Adel class group is. So that's the co-kernel of the norm map. And I would like to know that the Tate H1 is trivial, which Tate H1 is the regular H1. So that's really what I'm going for. I'd like to know, this thing is supposed to have a certain, the co-kernel of the norm map should probably be the degree of the extension, right? Like that's what we were sort of hoping for, at least for like a billion extensions, right? And then this first group we want to be equal to 0. So that's kind of where we're going. And we do that in several steps. So if you assume that it's cyclic, then we'll finite. Remember, there's a Herbrand quotient defined for cohomology of finite cyclic groups, which is just the ratio of any even-numbered Tate cohomology group to any odd-numbered Tate cohomology group. And the first step here is to prove that the Herbrand quotient is n, okay? And again, I'll preview it for you. It's going to turn out that the numerator has size exactly n, and the denominator has size 1. That's where we're trying to go. Okay, so yeah, this is a stepping stone to evaluating the numerator and denominator separately. Okay, as a corollary, this tells us that the co-kernel of the norm map has size at least n. So what's going on? So by Hilbert 90, we have that, the upstairs. I think maybe this is how I just stated this result before, but this really does follow from Hilbert 90, writing out the defining exact sequence for the Adel class group. Just 1 goes to L star, goes to I of L, goes to CL. You take Galois cohomology and apply Hilbert 90, you get that. Anyway, so what does that mean? It means that the Tate H0 here is this. It's Adel's modulo, modulo the norms from L together with the kind of principal Adels coming from K star. And so yeah, I'm not saying very much. What I set up here is that the ratio of this guy divided by this guy is equal to n, and therefore the numerator is equal to n times whatever the order of this group is, and so it's certainly at least n. Okay, we move on. Right, yeah, here we go. So this is one of the main results of the chapter where we're going for. So this is called the axiom of global class field theory. So it sounds important. Again, in the case where I have a finite cyclic extension, then I want the Tate H0, which as you see here is precisely the co-kernel of the norm map. So that's the thing that we were very interested in the local field case. So as I said, the co-kernel of the norm map for a cyclic extension at the moment is going to have size equal to the degree of the extension, and then we want the H1 to be trivial. Okay. And so what can you see from this? You can see that because we just computed that the Herbrand quotient was equal to the degree of the extension, you see this little arrow. Because of this result, these two statements are equivalent to each other because we know that the quotient is equal to the degree of the extension. So you can sort of have it either way. I think what we'll actually prove is that this one is trivial. Kind of makes sense. A little easier to prove that something is trivial than just show exactly how non-trivial it is. Okay. And so following Chevalley, this result gets deduced from results on Kummer extensions. Okay. And it's really just kind of a shame because this is a very beautiful development, and I'm just going to state like 1 or 2 results, and I'm totally gonna skip the proofs. And so you're seeing like the somewhere between like the skeleton and the corpse of this reasoning, right? So I'm just showing you some of the main pieces. Okay, so here's a result I probably should have mentioned before. If I'd mentioned in the last lecture, I probably would have proved it to you. This is Harari's Christmas theorem, 12.25. And so if you, this is just a result in global field theory. So if you take this is the S adels, but that's exact. I defined the S adels, which are the family of open subgroups that you get the adels by taking the limit of. This is exactly the same thing on the adels. So this is nothing that you haven't seen before. This is just give me the adels where they're units, they're in the local unit group away from S, and they're unrestricted when you're in S. So the assertion here is that if you take S to be a sufficiently large finite set containing the Archimedean places, then this S-adel group is large enough so that when you take the S-adels and you take the subgroup generated by the S-adels and the principal adels, then that gives you the entire adel group. Okay. I can't quite remember. I don't think I proved this in my number theory 2 notes, although I could be mistaken. The proof is given in Harari. It's not a bad proof. It uses the finiteness of the class groups of, let's say RS, the S integer ring. Okay, and so this is like a basic result about. If you remember when you're studying adels, you sort of realize that one of the things that you really want to prove is the the compactness of the absolute value 1 adel class group, right? That was kind of possibly arguably the main topological result about adels. And then in number theory 2, I explain that the compactness of the absolute value 1 adel class group is equivalent to the finiteness of the ideal class groups of S integer rings and the Dirichlet S unit theorem. Okay, so you can really go both ways. Okay, and so this is a result which is in that sphere of thought, and so you use the finiteness of the S class groups in order to prove this result. Okay. All right, and so now we develop some Kummer theory, unfortunately, kind of at warp speed. So Harari has a nice, he definitely takes a couple pages to set up some Kummer theory here. So if you take Kummer, remember, where does Kummer theory apply? Kummer theory is an explicit description of finite cyclic extensions of exponent n over any field which has a primitive n-through unity in the ground field. And the long and short of it is that if you have a primitive n-through unity in your ground field, then every cyclic Galois extension of exponent dividing n is obtained by adjoining nth roots of elements in your field. Okay, there's a more precise statement, but that's what's happening. Okay, so yeah, so suppose that K contains a primitive n-through unity, zeta n. Again, what's the point? So in fact, in the one proof that I am going to show you, if you don't have a primitive n-through unity in your ground field, well, you could extend the base to try to apply Kummer theory as long as the characteristic of your field does not divide n. Okay, so that'll come up later. So in characteristic 0, we may not have, your fixed global field is only going to have finitely many roots of unity, but over the algebraic closure, you can have as many roots of unity. You'll have all the roots of unity. Okay. Okay. So we take a Galois extension with Galois group Z mod n to the R. Well, evidently that's a wait, when I was saying cyclic, I think I didn't mean to say, I said cyclic before when I was describing Kummer extensions, and I should not have said that. This is evidently not a cyclic group when R is at least 2. So when I said Kummer theory describes cyclic extensions, I should have said abelian extensions of exponent dividing n. That's what I meant to say. So Kummer theory gives a complete description of the maximal abelian extension of any field, maximal abelian extension of exponent dividing n of any field containing a primitive n-through unity. Okay. Right. Okay. Okay. As I realize, we've already discussed a bit in this class. Okay. So so that's a Kummer extension, and then by this Christmas proposition. Just applied to the ground field, there must be some finite set S whose, so if you take the S adels And the principal adels, you get the entire adel group. If any such S works, then any bigger one works. So I'm not saying there's a canonical S, but you take one and let's take little s to be the cardinality. Okay, and now we have, again, these two results. This is where I feel bad because and obviously there's a lot going on here that is not being made clear in this very brief treatment. So the first result is that the number of elements you need to take in K in order to have that S-adel thing work is at least as large as the R here. This makes me a little bit worried. It doesn't quite make sense because I'm wondering if I've screwed up the K. Harari has a different notation. I kind of suspect that I've screwed up the K and the L. Let me look quickly at that. So that this just doesn't sound right when you apply it to K. So maybe I mean L. Okay. Seems to be right. Seems to be what he says. Anyway, let me just think about this for a second. All right, well, it seems to be correct. I find this, all of a sudden, I find the statement slightly confusing. The assertion that S is greater than or equal to R. So what is happening here? Think for a second. Well, we better just go with it. This is what happens when you just look at statements of results. But okay, I'm going to go with it for now. I find it confusing because it seems to me that if I choose a number field, for instance, with a primitive n-through of unity, there are certainly going to be Galois extensions with this Galois group for arbitrarily large R, and it seems like S depends only on K. So why is S greater than or equal? Anyway, whatever. I'll just go with that. Maybe if I figure it out, I'll tell you next time. So the result here is supposed to be that S is greater than or equal to R for some reason, and then there's a set of places in the complement of S of cardinality S minus R, so that this extension is, I mean, it's a Kummer extension, so it's obtained by adjoining nth roots of something, but this result is being more specific. So it's taking nth roots of things that are on the one hand S units, and on the other hand are nth powers at all the places in T. Okay. And then this is used to prove the following theorem under the same assumptions. This one is really not being swallowed by the treatment that we're giving. So I do the ST adels, these are the ones that are nth powers at S, unrestricted at T, and units away from S and T. And then I do the ST class group. So I mean, I should take that modulo K star, but how do I know the ST adels contain K star? So I throw K star in there. And then the statement is that the norm of the L class group at least contains this guy, and moreover, the index of this guy is equal to the degree of the extension. So that's true for any such extension, abelian extension of that form. If moreover the extension is cyclic, then good news, this weird ST class group turns out we have equality here. And that gives us the result that we want, because that tells us that for a cyclic extension, the co-kernel of the norm map is equal to the degree of the extension, which is kind of the key result. Okay, so yeah, obviously there's a lot being not discussed here. And again, I shouldn't keep, I'm really confused as to why in this setup, I didn't think about it until now, and now I'm confused as to why we're able to assert that S is always greater than or equal to R, but I'll come back to that. Okay, and so now, now we can prove, I mean, scare quotes, because I just blew through a bunch of results that I, certainly didn't prove. Now we can prove the main theorem, which was this global class field theory axiom, in the case where the characteristic of K does not divide the degree. So in particular, in the case of characteristic 0, and then Harari gives some more geometric argument in the function field case. So I remind you, what are we trying to prove? We're trying to prove that if you have a cyclic G-Galois extension, then the co-kernel of the norm on the class groups is equal to the degree of the extension, and the this kind of Hilbert 90 looking result that the first Galois homology of the class group is equal to 1. And so by what I said, by our previous result on the Herbrand quotient, we know that the ratio of these two things is equal to the degree of the extension, which before we called n. So we could prove either one. And so let's prove the vanishing one. Okay. And so this is a simple argument, but psychologically, you'll partially forget all the things we skipped before, and you'll think that we did something. Okay. So we go by induction on the degree of the cyclic extension. And so assume that this vanishing of H1 on class groups holds for all cyclic extensions of smaller degree. And so, well, the group theory of cyclic extensions is pretty clear. So I can certainly choose a sub-extension of prime degree. Okay, so I do that. And in fact, the more difficult case is when the degree is equal to that prime, because if that prime degree sub-extension is a proper sub-extension of my degree cyclic extension, then induction and inflation restriction is just going to do it for us. So this is nothing other than our old friend, the inflation restriction sequence. Okay, so I have a tower LMK, right? So the automorphism group of this guy is going to be a quotient, so I inflate that into the automorphism group of the whole thing, and then I restrict that into the automorphism group of the top piece, okay? And so what's the point? The point is that, I'm doing an inductive argument, and so my inductive argument precisely tells me that this extension, so L over K has degree n, and M over K has degree L. So this one, of course, has degree n over L. And so both L and n over L are smaller than n. So my inductive argument tells me that this one is 0 and this one is 0, and I have an exact sequence, so the thing in the middle is also 0. Fine. The more interesting case is the case where the cyclic extension has prime degree. Then I'm going to do some Kummer stuff. So I'm going to take K prime to be K adjoin a primitive L-through unity. This is exactly where I'm using, by the way, my hypothesis that the characteristic of the ground field does not divide the degree of the extension. Okay. So I do that, and then I base change my entire extension L over K so that it contains the L-throughs of unity. Then L prime over K prime is, you think a little bit just on field theory here, if I take a Galois extension of degree L, and then I join an L root of unity, to the top and bottom, I'm still going to have a Galois extension of degree L. Okay. And so L prime over K prime is going to be a cyclic Kummer extension, degree L Kummer extension. Well, I definitely just made the ground field have the nth roots of unity, so I can apply Kummer theory. And in particular, I can apply the theorem 13.21, which was applying to cyclic Kummer extensions. Okay. So cyclic extensions, when there are enough roots of unity, I just made there be enough roots of unity. And so, of course, I get the right result on the H0, and we already did the Herbrand quotient calculation, and that tells me the desired result after I make the base change. How do I get from the base change back down to the original? By the same kind of inflation restriction stuff. So certainly if you would join the L roots of unity, then you're trivializing the mod L cyclotomic character, which has target Z mod L Z star. So for any field extension and characteristic different from L, if you would join a primitive L roots of unity, the degree divides L minus 1, so is less than or equal to L minus 1. So that's less than or equal to n. So by induction, it must be the case that the result for this extension of degree smaller than L, which is n, has the vanishing of H1. And then the same inflation restriction argument that we did above is going to work to show that the automorphism group of L prime over K is equal to 0. I mean, it's basically the same, kind of the same picture here. So I have an L prime, and then I have an L prime, and I have a K prime, and I have a K. All right, and so I just showed, yeah. So then it's the same inflation restriction argument. So the H1 here is going to be in the middle of a short exact sequence involving kind of the H1 here and the H1 there, and both of those we just showed that both of those are equal to 0. Right. Okay, that's exactly what we just did. And so by the same inflation restriction argument, that means that the automorphism group of L prime over K is 0, and then I have an L in here somewhere as well. And so by another inflation restriction argument, that means that the automorphism group of L, the one with L over K. Okay, so this is a very simple proof. It's just using induction and inflation restriction. Okay. So but it's you see that we're reducing to the case of to the case of Kummer theory, which is a good, if you're studying abelian extensions, it's a reasonable idea to try to join enough roots of unity so that you can reduce to Kummer theory. Okay. So let's see. Yeah, so I have not too much more actually, because I've been going so quickly. So the next result is a very, very important and useful result, which doesn't really sound like class field theory, but the proof has something to do with it. If I have it's called the Hasse norm theorem. So if I have a finite cyclic extension of global fields, then you are going to be a global norm if and only if you're everywhere locally a norm. That's what the result says. Okay. So what does that mean more precisely? So you're a norm from L over K, if and only if for every place of K, you look inside the completion KV. And again, as I said before, because it's a Galois extension, whether you're a norm or not does not depend upon which upstairs place you choose. And so as long as you're a norm from every local extension, that will hold if and only if you're a norm from the global extension. Yeah, so I think, stop and think for a second. I think right to left is pretty clear. I think if you have, in general, if you're a norm from a global extension, then you should be a norm from every completion. So the right to left would hold, unless I'm really I haven't going quickly, but unless I'm greatly mistaken, right to left should hold for, I think, probably any finite degree extension. Okay, and so the important part is left to right. And this really is an exciting theorem because believe it or not, if you back away from cyclic even a little bit, this result does not have to be true. So the next question to ask is, if you have an abelian extension of global fields and you're a norm everywhere locally, does that mean that you're globally a norm? And the answer is no, not necessarily. Okay. What was I going to say? Yeah, so even you should think about this even for the case of like a quadratic extension of global fields away from characteristic 2, and sort of ask yourself like what local global principle is this telling you? Okay.
Pete, if I heard correctly, I think you said right to the left is the easy part. Is that what you meant?
No,
Okay.
left to right is the
Cool.
easy part. Right to left is the
I
hard
agree. Okay. Maybe I misheard. Good.
I don't know. Tyler's like, no, that's what you said. Okay, I didn't mean to. Left to right is fine. Much more generally, and then the other direction is the hard part. Yeah. Yeah, no, I mean, if you're sure. Okay. I'll say separable. For any finite separable extension, left to right should be fine. Let me just think about that for 1 second. Sure. Okay. All right, and so the proof of this does follow quickly from, it's not a bad exercise though, I guess. Okay, so the proof does follow quickly from what we've already done. So because it's a cyclic group, we have this twofold periodicity in the Tate cohomology. So I just proved that the first cohomology of the adult class group is 0. So also the minus first Tate cohomology. And then if I just take Tate cohomology again of the sequence of G modules that defines the L class group, well, the H minus 1 is 0 of that, and that means that this H0 injects into that H0. So that's what we got. So therefore, if you're a norm in every completion, then you're 0 here, and therefore you were 0 in that Tate cohomology group, which means that you were a norm there. Okay. So again, this is really a significant result. Okay. Useful, in fact. All right, and I'm almost done with this very quick lecture. Yeah, this is basically, this lecture is my take on chapter 13, by the way. And so, okay. So from this, we can bootstrap up a bit. So now it follows, you'll see, nice easy argument for any finite Galois extension, the H1 is going to be 0. Okay. All right. So why is that? Just by pretty easy stuff. So we just saw that this in the case where the group was cyclic, right? We saw that, and then we got even extra information about the norm cokernel in the cyclic case. So we'd kind of like to reduce to that case. So step 1, just reminding you of the undergraduate level theory of finite P groups. Using the class equation, you prove that a non-trivial finite P group, so a finite group of order a positive power of P, has non-trivial center. If you use that kind of inductively, then what does that prove? It proves that in any finite P group, you have a chain of normal subgroups, complete flag of normal subgroups, let's say. And so in particular, any finite, non-trivial finite P group has a normal subgroup of every possible order dividing the power of P, but in particular of index P, and therefore you have every non-trivial finite P group has a quotient of order P. And so this means that we can do the exact same Desvisage argument that we did before, right? So just as before, we were doing kind of induction on a cyclic extension. Because every cyclic extension of composite order has a proper quotient, the same thing holds for any finite P group. If the finite P group has order P, then of course it's cyclic, and we did that. If not, we do induction and sandwich it between a smaller quotient and a smaller subgroup. Okay. And so now we just have to do the case of groups that have several prime divisors. And this is exactly where some of this result in kind of CELO theory of Galois cohomology comes in. So for all primes dividing the order of my group, let's just choose a CELO P subgroup and let LP be the fixed field by the CELO P subgroup. Okay. And so, of course, Galois cohomology groups are torsion commutative groups. So we can always write a primary decomposition like this. And then by one of the first results that we proved on Galois cohomology of finite groups, if you restrict the P primary torsion, then the P primary torsion has no kernel upon restriction to the CELO P subgroup. Okay, that really was one of the first results that we proved, maybe in chapter 3 or something of this. Okay, and so we're trying to prove that this thing is 0. We did just a primary decomposition, and then each factor injects into the corresponding Galois cohomology, the CELO P subgroup, which is of course a P group. And so by step 1, that's 0. And so our guy injects into a direct sum of things, all of which are 0. So it's 0. Okay. So this is really the main result. This is if you sort of think back in terms of Tate-Nakayama stuff, I invite you to look back at the Tate-Nakayama theorem. So they're under certain hypotheses. If one of your cohomology groups vanishes for some module, and then in the next cohomology group, you have this like fundamental class that has this really nice property upon restriction to certain nice subgroups, then cupping with that fundamental class is going to give you an isomorphism. So that's the very broad form of the Tate-Nakayama theorem. And so if you look that up, we've set up half of it because we've proven the H1 part. And so now we should be investigating the second Galois cohomology of the Idel class group and kind of looking for the Tate-Nakayama class. And just as in the case of this is not literally the multiplicative group of the global field. It's something which is, more complicated, but works better Galois cohomologically, but that's where we're going. And so to understand the second Galois cohomology of the Idel class group, that is going to involve a discussion of the Brouwer group of the global field. And we'll tear through that in the following lecture. So that's chapter 14. Once we have that, then we can plug into Tate-Nakayama, and then at least we'll have a reciprocity map, and then we'll have to say all these things about, how do we prove the existence theorem and global class field theory, blah, 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 blah. Okay. So again, I apologize that this is going so quickly, but it is. Okay. Any final questions? All right, well, we'll blow through more stuff next time. So see you soon.